So we've actually come to the end of the geometric optics part of this course, and this is the last lecture that we'll do on the geometric optics part. So I wanted to end with a discussion on some phenomena that you can see and some applications that can be explained using just geometric optics and not wave optics. This is a photograph that has been taken from underneath the water. So that you have a diver swimming on, closer to the surface of the water, and there's someone below this person who has looked up outward and taken the photograph. Now, what you should notice is this is not a feature that's been added. This naturally arises when you look at a photo that has been taken from inside the water looking out. You'll always see this dark circle around. Okay. Now, knowing what you now know, can you try to figure out where that dark circle arises? Why that dark circle arises? This is a completely geometric optics phenomena. So if you're trying to tackle this, if you're trying to figure out how to solve this, a good place to start is to try to draw a schematic of this. So what do you know for sure about the system I'm giving you? Well, there is water and there is air. So you can start by drawing a sideward look where you have air and you have water. Can you give me one key word you think might explain total internal reflection? Okay. Now, it's not exactly total internal reflection that's happening here because the light source is outside. There's no light source in the water. You're capturing this image from light that's coming from the air, from the rarer medium to the denser medium. But it is the same reasoning, the same reason you have total internal reflection is why this happens. So let's look at this a little more detail. So anytime you're given a geometric optics phenomena or event to explain, start with the ray drawing, right? And usually the ray drawings are just going to follow Snell's law and trigonometry. Right? So start with the ray drawing, however hard it may seem. Start with the ray drawing. Okay. So if in the case that in the previous photograph, someone is taking a photo looking up, right? So they're in the water, they're in the denser medium, and they're looking up. Now, let's just look at how light enters the water. The light source in this case is definitely outside, right? How does light enter the water? If you take this ray number 1, right? When it enters the medium, since water is a denser medium, it's going to bend towards the normal, so it has a smaller angle over here. But as you go on increasing the angle of the incident rays, so this goes on increasing, while in every case, the ray of course bends towards the normal. If you have a larger angle here, you also have a corresponding larger angle over here, right? And at some angle, the ray is, so what is of interest to us is why do we have that dark circle? Okay. So this is just to remind you of Snell's law. As you have a certain angle over here, you're going to have a smaller angle over here, right? Okay. Now, what happens in this air-water case? These are all the rays coming in from the sky. So I have rays that come in from the entire 180 degrees. The normal incident ray carries on no deviation. This ray deviates slightly. This ray deviates and comes in at this angle. Now, I cannot have an angle greater than 90 degrees. So, I am capturing all of the light. I'm not losing any of the image. But the entire image that was, or the entire object, if you will, that was spread across 180 degrees in air is now bending. All the rays from that 180 degree cone in air is now being bent as it enters the water, and it only, if I assume this as refractive index 1 and this is 1.33, I have a 97-degree cone over here. Okay? So, very, very careful with what you're seeing. It's not, the dark circle doesn't mean that you have cut off anything in your image. It's not that light is blocked. All you're saying is because of Snell's law, the light that comes in at 90 degrees, it gets bent and comes into the water at a smaller angle. So this entire range is compressed into a smaller cone of light. But of course, inside the water, you can see the full 180 degrees. But you will only see the image in this region, and so therefore these regions will appear dark. You can think of it like this. If the light source were here, say the light source, so this is water, this is air. If the light source were in the water, of course, the normal ray would continue through, but the ray incident at some angle would get reflected, right? And there would be some angle but there would be some reflection, there would be some transmission. But at some angle, you would have all of the light reflected. Let's say this is theta c, and there would be no refraction. Right? We know light rays travel reversibly. So although in this case the light source is outside, exactly the same phenomena is happening because the light is coming from the rarer medium. All of it refracts. The rays here, there's no total internal reflection here, because that's the rarer medium. Total internal reflection happens only if the light is within the denser medium. This is a rarer medium, so there's no total internal reflection. Everything transmits, everything refracts through that interface, the air-water interface. But it bends, and thereby the cone, which could have been 180 degrees in air, has a smaller value in water. And the result is that whenever you take a photograph in water looking out, you're always going to have this dark ring. Okay? Now, this particular photograph doesn't really have a lot of detail. All you're seeing is actually just the diver who is in the water. But I could have had a scene, so I have a pond, and then I could have had trees over here. Maybe something leaning over like this, right? I should be seeing all of that in the photograph. We are not saying that, let's say something was hanging over here. You would see this. So let's say I have different images, different objects. The object B would probably appear clearer than A, because A is coming in from that glancing angle. So the amount of light coming in, remember Snell's law doesn't tell you anything about the magnitude of the light coming in. It just tells you the angle. If light is coming in at a certain angle, this is the angle with which it will refract. Does not say that 100% of the light refracts 90%. Snell's law doesn't tell you that. You have to go back to Maxwell's equations to get that. We know that the amount of light that refracts or reflects changes with the angle of incidence. When do you have the best reflection? The closer you go to glancing angle. Right? You can take even your notebook, hold it up at glancing incidence, and it's almost like a mirror. It's very reflective. It's very reflective when you're looking at very large angles of incidence. If more light is being reflected, it means less light is being refracted. So the amount of light coming in from this magnitude is much less than the amount of light coming in like this. Okay. So if you had a lot of objects outside around this water body, the objects that were in the center would probably be much clearer than the ones at the side, because the amount of light you were getting would be much larger from those objects. But having said that, people often get confused and think this black ring means we've cut out. You've not cut out. You have the full 180-degree view. It's just that it's been compressed into a smaller cone. Right? You can think of it as some kind of distortion. Right? Because what should have been in this much area has now been squeezed into smaller area. Okay, this is called, unsurprisingly, Snell's window, because you can explain it completely by Snell's law. And do go look it up. You get some really, really beautiful photographs that have been taken. It's, again, you're not doing anything special to get these photographs. It comes automatically because of the way light refracts. Okay. So that's just a phenomenon. But geometric optics, why do we spend 5 weeks, 6 weeks studying geometric optics? And in fact, you could do an entire course on geometric optics. We use geometric optics because many real everyday systems, applications are based completely on geometric optics. And one very important one to do with security is the fingerprint sensor. Okay, so this is an image of my finger. Now, it's very easy for me to take this photograph. In fact, today I just pull out my phone and I take a photograph. But it's not easy to see the fingerprint at all, right? And if I want to use this or use the fingerprint and store it somewhere and then have it stored against maybe the entry of a doorway so that we can check the fingerprint and then open the door based on that, or for your Aadhaar cards you had to do that. How do you get the fingerprint? Now, why is the fingerprint not easy to see? Why is the pattern of those whorls and curls not easy to see? And to answer that, one really has to look at what do we mean by imaging. Okay, I keep asking you this question at different points in the course to focus on some particular aspect of imaging. Okay? So in this case, I'm asking it because I have this image, but I want to have images like this. Okay? So in effect, I'm asking you, what's the difference between the photograph of my finger and these images down here? What's the big difference between them, right? And the answer to that is contrast. And a large or a very important aspect of any imaging is that your image must finally have very clear contrast in it. Now, this is a picture of India Gate taken, and so I chose Delhi because if you want to have poor contrast, you have so much pollution over there. It's easy to get images with poor contrast. So I am telling you there is India Gate over there, but you can almost not see it. The visibility is very poor. The result of that is there's no contrast between the region around the structure and the structure itself. And the effect of that is you don't see the structure itself. Okay, and if your goal was to take a picture of the structure, you have not achieved it here because there isn't enough contrast in this image for you to make out the difference. Imaging is successful. A good image allows you to see something because you see the difference between different points or different places of that image. If everything looks the same, even if there's information there, you are not able to ascertain that information. Okay, that's why imaging things like cells is so hard, because there are slight refractive index differences. There is a difference. It's not that you're imaging a surface or an object where there is no difference. You're not taking a homogeneous, uniform object and imaging it. You're taking an object which has a lot of variation, and that variation can convey a lot of information to you. So if you're looking at cells, you could be able to make a diagnostic out of that by saying this cell has this problems and therefore it means this person has this disease, or this medicine is working or it's not working. So there's a wealth of information there. But because that information lies in very slightly varying refractive index, you are not able to see that difference. And if you can't see the difference, as far as we are concerned, that information isn't there. Okay, so a good imaging system needs somehow to extract that information. So the same photograph taken on a clear day, and you can see now there's a big difference in contrast. So it's obvious that you can see the structure in the lower picture because of the contrast, the difference between it and the air around it. So in the fingerprint sensor, we aren't able to see the print. In the photograph of the fingerprint, you're not able to see the print because the contrast between the ridges and the depressions of your finger, that difference is too small for you to make out. Okay, so it looks like almost a continuous surface. You can make out there's some faint structure there, but not clear enough for you to get these nice clear patterns as shown down here. Okay, so if you want to make a fingerprint sensor, you want to somehow enhance those differences. That would be the goal of a fingerprint sensor. Okay, how many of you did a Aadhaar card registration? So what did you have to do for the Aadhaar card registration? One of the biometrics was you had to have your fingerprint taken. How did you do that? So you had some glass surface, you had to press your hand. How many of you had to do it multiple times because it didn't work the first time? Right? What did they ask you to do between? Did they ask you to do something? They made you clean your hands, okay? So sometimes there's grease over there, right? And that is one of the reasons. So even though, so that we're going to learn about that system that helps enhance the contrast. But that system also cannot work if there is the natural, whatever oil, natural oils are there, but that lies between the ridges and that works to lower the contrast. So the hand sanitizer helps to remove that and allows the machine to enhance the contrast. Okay, they might have also asked you to press quite firmly, right? All of these are ways to help the tool enhance the contrast. Okay? Now, this is roughly, it's a very simple system. This is roughly how it's working. So you have a light source, it's not a bulb like this, but it's a light source. And you're going to press your finger. So this is the surface, you saw this surface. Okay, I'm going to ask you soon why you have a prism like this, but you would have just seen the upper surface of the prism. You press your finger down upon or your fingers down upon it, and then the light that is reflecting off this is being collected by a lens and being collected by a camera and giving you that image. Okay, so this is the basic anatomy of most fingerprint sensors. Now, how exactly is this working? If you remember the image of India Gate, whoever's taken the photograph is standing in front of the structure, and whatever ambient light is there is using that ambient light, it's reflecting off the structure and being collected by the camera, and it's forming the image. So the reflected light is being used to form the image. So it looks like at first glance that all I'm doing here is creating a system that will reflect light off the image, of the finger. So why should that make any difference? I should again just get the image that I had got off my entire finger without the fingerprint being. How is this enhancing contrast? Okay, that's the question that you have to ask. So if you look at it in a little more detail, now forgive this finger, it's not a diseased finger, it is my attempt to show you a finger with the detailed fingerprint so that we can understand how geometric optics is working over here. Okay, we use the prism because we want to send light from the source onto the finger, where the region where we want to image the print. Now, why do I want the light to be incident on the surface of the prism like this? Why couldn't I have this is a finger and this is my block of glass block. Yes, so here I want light to go through this, but I want, if I send light through this structure, there's always going to be reflection here. There's always reflection. The amount of reflection over here is minimum because the incidence is normal. So if in a normal air glass interface at normal incidence, if you've not done anything to the glass, if you've not treated it in any way, at normal incidence, you have 4% reflection. And the amount of light that's reflected goes on increasing as the angle of incidence goes on increasing. So here, because the surface of the prism, because you're using a prism, the normal is, this is the normal. So here, I'm sending in light along the normal, which means I have the minimum reflection of 4%. So I'm losing the minimum amount of light by having that incoming surface along the same direction as the light. Okay, so that's why we use a prism. Now, it's incident on the finger and it's reflecting, but it's not reflecting the same way from the regions where the ridge touches the finger, touches the glass plate, and regions where there's an air gap. So you can think of this as an air gap. And that's why you want this to be an air gap, not an oil gap, which sometimes they ask you to wash your hands to remove those natural oils. Okay, so let me get rid of. Okay, so what is happening is I can consider the refractive index of these regions to be air. The refractive index of the prism itself is glass. We now are sending in light. So this is the reason why you press the finger against a glass object, because we are now setting up the condition where total internal reflection could happen. Right? Total internal reflection cannot happen. The incident medium is a rarer medium. So I have now set up, so using Ng greater than Na, I've already written that here, I am allowing total internal reflection to occur. Okay. But does total internal reflection occur everywhere? I have regions where I have the glass and I have air. And then I have regions where there's glass and there's the finger. So in some places, the refractive index of the first medium is larger than the second medium, and in other places, the refractive index of the first medium is not larger than that of the second medium, or the difference is much smaller. Now, how did I start this whole discussion? I said somehow we need to enhance contrast. And the previous sentence should make it clear how we are enhancing contrast. In some places, the conditions are perfect for total internal reflection to happen, and in other places, they are not. So yes, we are using reflected light, but we are using totally internal reflected light, and in some regions that total internal reflection is not allowed to happen. And that's why it's called frustrated total internal reflection. And it's that difference which is enhancing contrast. So I would have total internal reflection happen in this region and it will not happen here. I'll have total internal reflection happen here and it will not happen here, and so on. And therefore, the reflected light, it's strongly reflected in some places, it's not reflected in other places. And what dictates where it is reflected and where it is not? It is the structure of the fingerprint. And that's exactly what you're trying to image, right? So, you're going to then get an image where, yes, you get reflected light, but you get reflected light from some regions of the print, not from other regions of the print, and that's where the contrast comes in. Okay, it's very, very simple idea. But that's good because you want the fingerprint sensor to be extremely simple. You should be able to make it fairly small. It should be lightweight. You should be able to very simply capture those fingerprints. Okay. So we can do a demo of this, and that's what I want to do now. Right. So I'm not sure if you've noticed, but anytime you're holding, so anytime you have a fingerprint sensor in your hand, every time you hold a glass, and it works better with cold water. So all I'm doing is, I mean, you might have noticed this effect. Anytime you have a glass of a liquid, and a colder liquid helps. I am not going to do the next example. I'm just going to give it to you for you to figure out. But in most cars, you always have, the driver has a rear view mirror, the mirror that's within the car. And this allows the driver to see the traffic behind. So you can adjust this mirror, and it's called a day-night mirror because during the night, the car behind you, of course, will have the headlamps on. So if the mirror setting is the same as it were during the daytime, the bright headlamps of the car reflect directly into the driver's eyes, and of course that's not good. So the mirror has two different settings. You use one setting so that it works during the daytime and gives you a good image of the car behind, or traffic behind. And then you change the setting. You still want to see the traffic behind, but you don't want to see the headlamps of the traffic behind. And so you flip the angle of that rear view mirror so that it's different for the day setting compared to the night setting, and it allows you to see the traffic behind in both cases, but it ensures that you don't get the headlamps during the night time. So I've just drawn these images like this here, and now I want you to go and figure out. So that's an exercise I leave to you to figure out how it works. Okay, so his question is, how do we see the fingerprint? So how do we see that? The water and the glass is acting exactly like the glass prism, right? So you have the glass and the water that is acting like the glass prism of this design. So I'm pressing my finger against it. That's why you look from here, because there's light coming in. It's hitting the region, the surface of the glass where your finger is. Doesn't help if you look like this, right? Because I'm not getting the effect of the light hitting that particular region and seeing the total internal reflection. So when I look from here, the light is entering the water surface. It's not the best, and I don't have normal incidence. So there I'm losing some light there, but that doesn't matter. Light reaches the finger, reflects off the finger and comes to my eye. But total internal reflection is occurring there. And it's only occurring in regions where there is a water, glass, air gap. And where the ridge touches the glass, then I have water, glass, finger. So the refractive index difference there is not the same as water, glass, air. So the reflection that's coming back is different from different regions of the fingerprint. And that's why the contrast is enhanced. But yes, you should think about it in more detail, exactly how this works. But this is the basic principle. Okay.